Welcome back to section 6 of chapter 2. In this section, we're going to be looking at estimation and application of derivatives. This section, there's going to be a lot of topics, but not a lot of new stuff. It's just how do we use the stuff that we already know to do new things. So the things that we're going to look at is rates of change. Now there's two different types of rates of change. There's the average rate of change, and there's instantaneous rate of change. The average rate of change is the slope between the endpoints. It's the total change in y divided by the total change in x. A lot of times that's change in distance divided by change in time, but not always. An example of an average rate of change was as I was driving to school this morning, it took me 30 minutes to drive 22 miles. My distance was 22 divided by half an hour. I drove an average of 44 miles an hour. Now that doesn't account for speeding up and slowing down and stoplights and things like that. It's just, it took me half an hour to drive 22 miles. The instantaneous rate of change is the derivative at that point. That would be like how fast was I driving when I entered the intersection at Terry's Corner. That would be an instantaneous rate of change. Like, what is my velocity? What is my speed at that point? So, to find these, we're going to look at a problem. A particle is moving along the x-axis in such a way that its position can be modeled by the equation x of t equals t squared minus 4t minus 5. How far does it travel from t equals 1 to t equals 3? That should be t equals 3 to t equals 5 seconds, just like it is down here. What is the average velocity, and then what is the instantaneous rate of change when t equals 2? We'll go when t equals 3 on that one too. Sorry, I'm changing the example on us. So, to figure out how far it went does not take calculus. It takes subtraction. We're going to figure out what the position was at 5, we're going to figure out what the position was at 3, and then we're going to subtract those. That's the change in position. So, to figure out what these are, we could have x of 3 equals, then we just plug it in. 3 squared is 9, minus 4 times 3 is 12, minus 5. So x of 3, 9 minus 12 is negative 3, minus 5 is negative 8. And then x of 5 is going to be 5 squared is 25, minus 4 times 5 is 20, minus 5. Well, x of 5 is going to be 0. So how far did it move? How far did it travel? Well, 0 minus negative 8. It traveled, it went 8. Do I have units, meters? We'll say meters. It went 8 meters from time equals 3 to time equals 5. Now, what is the average velocity? The average velocity is going to be the total distance that it traveled in that time interval divided by the total time. The total distance was 8 meters divided by the total time from 3 to 5. That's 2. That's just 5 minus 3. And 8 over 2, the average velocity is 4 meters per second. We'll say it's seconds. So that's the average velocity. Notice no calculus happened in that problem. That we found the slope between the two endpoints. It was y minus y over x minus x. We just did the y minus y part over here. We didn't have to have that question beforehand. But a lot of times, especially when we're starting out, we will have that question. And now the instantaneous rate of change. The instantaneous velocity, instantaneous rate of change, we need the derivative. X prime of t is going to be 2t minus 4, and then we want to find it at t equals 3, not t equals 2. If t equals 2, it would have just been 0. T equals 3 puts it at the beginning of the interval. That's why I changed that. So x prime of 3 is going to be 2 times 3 is 6 minus 4 equals 2 meters per second. So that's the instantaneous velocity. What this tells me is that from 3 seconds to 5 seconds, it increased speed because that made its average 4, which a lot of times that'll happen if we're dropping a ball. It's going to be going slower at 1 second than it will be at 2 seconds. So those are our rates of change. And velocity, by the way, something we'll be working on a little bit here and there. Introduce it now, we'll be coming back to it again over and over, is speed. Velocity is directional. It could be positive, it could be negative. If it's falling, it's probably going to have a negative velocity. In a problem like this, where we have a particle moving along the x-axis, which is actually, it's a very common problem, but it's actually a very applicable problem. It's just a single dimensional movement. A negative velocity just means it's moving to the left. A positive velocity, it's moving to the right. So that's velocity, it's directional. Speed is the absolute value of velocity. Speed is just how fast is it going. It doesn't matter what direction it's going, how fast is it going. So speed it's the absolute value of velocity. So our next topic here is estimating with a table. So sometimes when we have a function, we don't know what the equation is. All we have is a table of values. And so we're going to be able to estimate the derivative from the table. And remember, the derivative is just a slope. So we're going to find the slope, we're going to estimate a slope using points in a table. Now, it takes 2 points to estimate a slope. And so we just need 2 points. So an option we could use is we could use the 2 points where we have the point we're looking at. So this is the tangent line right there. And I have this point and that point. So is that slope close to the slope of the tangent line? Not particularly. Well, let's use the point on the other side. So again, the black line, we have the tangent line. And now we're using these 2 points. But does that slope represent the tangent line very well? Not particularly. There is another option. Instead of using the point we're looking at and one of the points on either side, use the 2 points on either side. So we have the tangent line and then these two. Is the slope of that one the same as the slope of the tangent line? Probably not, but it's going to be pretty close. It's going to be closer than either of these other two. And so what that means is that when we have a table of values, if we're looking for the slope at this point, we're going to find the slope between the points on either side of it. Now, we don't know what the function looks like, but most of the time, and with what we know, this will be the best estimate of a slope that we can get. So if we want to use the distances to estimate the derivative, velocity at t equals 2.2 of this information, so 2.2 is that one, we're going to find the slope between these 2 points. So to do that, we just subtract y minus y. So f prime of 2.2 is going to be about equal 9.3 minus 7.8 over 2.3 minus 2.1. 9.3 minus 7.8 is going to be 1.5 over 0.2. And then 1.5 divided by 0.2 is going to be about 7.5. So f prime of 2.2 is going to be about 7.5, then add units. It doesn't tell us what it is, but like feet per second. And so that was using a table to estimate the slope at a point, estimate the derivative at a point. This was another of those topics. This doesn't actually involve calculus. The idea that we're going to use those points to get a tangent line, that's calculus, but the actual computation part of it is not calculus. And it's not particularly difficult. The hardest part is simply knowing what two points to choose. Now, if we were trying to find the slope at an endpoint, let's say we're trying to find it at 1.7, we would have to use those 2 points because we don't have another point on the other side of 1.7. So if that's the case, you just use that and the one next to it. But most of the time, we'll have a point on either side. Use those 2 points. So that would be estimating with a table. Next one, finding tangent lines and then linear approximation. So to find a tangent line at a point, that's the same as find the equation of a line, any line. The two things we need to find an equation for a line are a slope and a point. So for a point, we're just going to plug it in. We want when x equals 2, f of 2. So we're going to have 2 cubed, that's 8, plus 2 times 2, which is 4. So f of 2 equals 12. We have a point. For the slope, we find the derivative. F prime of x equals 3x squared plus 2. And then f prime of 2, because we want it specifically at that point, our slope is a number. We plug in 2. 2 squared is 4 times 3 is 12 plus 2. Our slope is 14. So we have a slope and we have a point. Write the equation. Y minus the y part of our point, 12, equals 14 times x minus 2. At this point, we would usually write it in slope-intercept form. We don't particularly want to put it in slope-intercept form because of the approximation part of this, but we can move this 12 over. Y equals 14 x minus 2 plus 12. So that's the equation of the tangent line. Did that take calculus? Yes, it did. We had to find the derivative. But once we found the derivative, actually writing the equation of a line, that's something you've been doing since Algebra 1. So now using that to approximate the value of f of 2.1, we're going to plug 2.1 into our tangent line. So now the tangent line, it's going to be exactly on the point at 2, but then the function is going to curve away. The line's going to go straight. As long as we're really close to 2, it's going to give us a pretty good approximation of what we're looking at. And this was a skill that was very, very useful back before calculators were common. But even still, we use it in some higher level math. We'll use this idea when we're dealing with slope fields to use the Euler method of drawing a particular graph on a slope field. It uses something like this. And then other things when the calculations are actually too complex for pretty much anything, linear approximation gets used. And so we're just going to plug this into our equation. So f of 2.1 will be about, we'll have 14 times 2.1 minus 2 plus 12. So f of 2.1 will be about 2.1 minus 2 is just 0.1. That's why we leave it in this form. 14 times 0.1 is 1.4 plus 12. So f of 2.1 is going to be about 13.4. So that's going to be close to if we just plugged it in, but it probably won't be exact. I mean, it would be very surprising if it was exact, but that gets us close. It gets us a linear approximation. And so that's that topic. That part of it doesn't require calculus. The only calculus that we did on this page was right here when we found the derivative. That was it. Everything else is just applying the algebra that we already know to do these things that we already know how to do, just with a possible different context. And the next topic that we're going to look at is about maximums and minimums. Now, this is something we're going to touch on briefly right here. We're going to be working with it a little bit off and on, then we'll come back to it hard again in chapter 4. But maximums and minimums are one of the reasons where calculus is amazingly useful. Because if we have an equation, a function, say it looks something like that, our maximums and minimums, these guys all have something in common. And we saw this when we were looking at the sine and cosine functions. And what they have in common is that the slope goes from positive to negative, and in between, our slope hits 0. So at maximums and minimums, f prime of x equals 0. So if we want to figure out the maximum position something hit, figure out when is the velocity 0, when did it turn around? That'll get us the maximum or minimum position. But it's not just with velocity, it's with any function. The maximum minimum values always have to happen when the derivative equals 0. Now that doesn't mean that they always happen when the derivative equals 0. It is possible for the derivative to equal 0 without it being a maximum or minimum. For example, if we take an x cubed function, looks kind of like that. Right here in the middle, the derivative equals 0, but it keeps going. It keeps going up. It's not a maximum or minimum. Because if we think about it, if we take the derivative of x cubed, we get 3x squared, which is always positive. It is always increasing. The slope is positive. If the slope's always positive, it's not going to hit a maximum because it's going to keep going up. And so that is something that we'll have to look at and catch later on. We'll see that later on. But right now, you're just looking for maximums and minimums. You want to look for when the derivative equals 0. And again, we'll get more on that later, and we'll be using a lot of these topics actually continuously throughout. Like we'll have some linear approximation questions on most homework assignments. We'll have finding maximums and minimums. We'll have tables. We'll have things like this just popping up here and there with all the stuff that we do. So with that, keep working problems, keep asking questions, and as always, happy mathing.